Okay, so now we are going to start something totally new, but it's actually we're using random matrix theory to prove the results. So this is Euler characteristic. This is a very well-known result due to Harer-Zagier. I believe around 1985, the current paper was published. And so we are following to some extent the thing that we have in Ettinghoff's paper. See also Ettinghoff notes. Okay. So let me give you the theorem that we want to prove. And then we will try to unravel different pieces of the theorem, define the concepts that's involved, and then we go from there. So the theorem that we want to prove is the following. This is Harer-Zagier theorem. So let MG1 be a moduli space of closed Riemann surfaces genus G.
What is a moduli space?
I will come to that. Exactly, that's the point. Yeah, Riemann surfaces of genus G with one marked point. So this is you can think of it for now just as a topological space is a space, it's a thin space. Then the Euler characteristic of MG1 is isomorphic to negative zeta function at 1 minus 2G. I'm trying to, actually there's no negative. Okay, so this is the formula. Now let us unpack the meaning where chi is actually is the orbifold Euler characteristic. Is orbifold Euler characteristic. Of course, Euler characteristic itself, the original one we have seen appearing in our formulas, but this is the little refined version. It's called orbifold Euler characteristic, and zeta Z is a Riemann zeta function. Riemann's the function. Yeah. Okay, so I believe that's all.
So
I want to.
this always called other characteristic, some sort of characteristic class, or
Yeah, it is. Yeah, it's but it's a bit refined because the Euler characteristic is just an integer the way we define because it's alternating sums of Betty numbers of the space, but this could be rational, so it's a bit more sophisticated. But that's because this is not quite a manifold. There are some singularities here, and these singularities are reflected in the fact that the sky will take rational values as well. Right. Okay. So, right. So then what we have to do now is to unravel different pieces of this. Actually, the way we prove it is that we're going to show, so this is a standard fact. The Riemann zeta function at 1 minus 2g is actually equal to Bernoulli number. Do I have negative? Yeah, negative b2g over 2g, where b2g, or actually bn, actually n from 0 to infinity, or Bernoulli, yeah, numbers. Okay, so maybe the easiest place to start is to understand what these Bernoulli numbers are a little more to get familiarity. So let me tell you what these PNs are. So definition of Bernoulli numbers. So these numbers are defined through the generating exponential generating function. Okay, they have a exponential generating function. So x over e to the x minus 1 is equal to sigma bn times xn over n factorial and from 0 up to infinity. Yeah. This is the so if you want, this is the definition of Bn. This is a nice function. This function is smooth at 0 also. Because this, if you take the limit, this is 0 over 0, you can use L'Hopital rule. And then you take you see that the value of this function at 0 is 1. So this certainly tells you that E0 is 1. Okay? The constant term of the series is 1. So B0 is equal to 1. The name of actually x over e to the x minus 1 as x goes to 0 is equal to 1. This implies that B0 is equal to 1. Now, compute B1 and B2 and B3, you have to, I mean, the most straightforward way, according to the definition, is just to divide this power series by this power series, and you can divide. That's not a problem.
Differentiate and put x is equal to 0.
You can do that as well. Yeah, you can do that as well. But yeah, so you just do that, and so let's see what is B1. Let's compute B1. So to compute B1, I have this series x over e to the x minus 1. If I just compute e to the x minus 1, it's going to be what? X plus x2 over 2 factorial plus x3 over 3 factorial, right? Because 1 cancels here. So nice. Now I can simplify x. So this is equal to 1 over 1 plus x2, 1 plus x over 2 factorial, right? Plus x2 over 3 factorial. Okay, so then I just use the power series expansion, 1 over 1 plus y equal to 1 minus y plus y2 minus y3, so on. The geometric series implies that 1 over 1 plus x over 2 factorial plus x2 over 3 factorial, so on and so forth, is equal to 1 minus this one, 1 minus this guy, x over 2 factorial. Yeah, plus x squared over 3 factorial, so on. And this is just y. And then we have to put y squared. This is y, right? And if we raise this power 2, the least term is going to be x squared. So x over 2 factorial remains. So it's going to be equal to 1 minus x over 2 factorial plus some other terms. So what does this mean? This means that B1, according to our definition, is minus 1/2, right? So we conclude that B1 is minus 1. So the conclusion is that B1 is equal to 1/2. So we have these two Bernoulli number values, B0 and B1. Yeah. So one thing we can say in general about Bernoulli numbers is that actually after 1, all higher odd terms are 0. So there's a lemma. Let me write the lemma here. The lemma is there. So 1 is that, first of all these Bn's are rational numbers. This is kind of obvious from the definition. Bn's are rational numbers. The second statement is that b to n plus 1 is equal to 0 for all n bigger than or equal to 1. So the odd Bernoulli numbers after the first one are all 0. Only even remains, and they are related to the zeta values like that. Okay. So prove 1 is obvious. I mean, from the definition. The second one is a bit tricky because we want to say, yeah, this function is all these things. We cannot take derivatives. Or that method also doesn't work. So can you suggest a way to approach it? So we have a power series that we are saying whose odd terms after the first one are 0. We want to show that this fact for this power series. So the best way is to do that is to subtract the first two terms, the 0th order term, first order term, subtract it. So we are saying that the remainder is an even function. So we just consider, this is the proof, x over e to the x minus 1 minus, the first part is 1 minus 1/2 x, right? This is the first two terms of the power series. If you subtract it, the remainder is an even function. We want to say that it's an even. It is even. Yeah, so how do we do that? So let's get this now, x over e to the x minus 1. Minus 1 plus 1/2 x. Okay, so this is equal to. So what's the best way to show that this is even? Well, I replace x by minus x and I have to show that they're equal. So yeah, so this is the question. Is this equal to negative x over e to the x into negative x minus 1 negative 1/2 x, right? That's what we want to show. Okay, so to prove that, we can multiply this by, yeah, e to the x, I believe, if I factor e to the x here. So how can we approach that? Yeah, so I just multiply this by e to the minus x on the left-hand side. Yeah. So left-hand side is equal to, if I multiply by e to the minus x, I'm going to get x e to the minus x, and here is cancelled. It's 1 minus e to the minus x. Minus 1 plus 1/2 x, so that's equal to 1 minus e to the minus x, right? And then I've got x e to the minus x. And then I multiply, I get minus 1 plus e to the minus x. Plus 1/2 1 minus e to the minus x. Yeah. So what happens now? Well, this is, I can just write it as negative 1 minus e to the minus x, right? And then there is, this simplifies, it just gives me negative half of, so this whole thing is negative half of 1 minus e to the minus x. Okay, so I don't have enough space here. This is tedious now, but you can do that. Okay, so I'm going to claim it. Again. the margin is not large enough to write down the proof. But I don't know any other way. It's a very important fact, but it's yeah. So that's what we know about Bernoulli numbers. Now, how these? So let me tell you a little more about, because this is one of the most important number sequences in mathematics. It appears in many places, in physics, for example, in combinatorics. Yeah. The first time they appeared, it was actually discovered by Bernoulli in Oliver form. So Bernoulli for Haber formula. So this was a problem that everybody tried to solve in late 17th century. The problem is when you give me a formula for 1 to the k plus 2 to the k plus 3 to the k plus n to the k. A closed formula for this. So power sums basically, right? So power sums. And we can show that actually this always starts with, this is a polynomial in n of degree k plus 1. And it always starts with n to the k plus 1 with this coefficient. The next one is 1/2 n to the k. And these are constant, so always the same. And the next term is 1/12 n to the power k minus 1. Actually, k plus 1, I believe. The power 12. You just change. You must have something. Yeah, k over 12. So I can't give k over. And this 12, 1/12, is actually beta. And then all these lower order terms are expressible in terms of Bernoulli numbers. So you can read it in Wikipedia. So express as sums of terms with Bernoulli numbers E, 4, E, 6, etc. as coefficients. I mean, there is next term which is n to the k minus 2, and there is some Bernoulli number here before, and then some rational function, some rational number, which I don't, but this is later. Okay, so yeah, this is people were really wasting, I'm not wasting, really were working hard to find a formula for this. Bernoulli guessed the form, but he didn't prove it, but it was proved much later by Jacobi. Anyhow, so that's the way that that's Bernoulli numbers. I hope you see Bernoulli numbers in another applications in your life, because that's such a joy to see Bernoulli numbers. Now, zeta function is Riemann zeta function, and this formula actually is quite remarkable. Let me tell you why. This is the formula that this is equal to the expressible in terms of Bernoulli numbers. Let me tell you just a little bit about that, and then leave this aside. Yeah, so okay, so now we have Riemann's zeta function. So very quickly, because you know this, so zeta of S is equal to 1 over 1 to the S plus 1 over 2 to the S plus 1 over 3 to the S. Right? This is Riemann zeta function. This is originally defined for real part of S bigger than 1 because of the P series test. And for real part of S bigger than 1, this is absolutely convergent and is uniform convergence on compact substance. It's absolutely uniformly convergent on compact subsets of real part of S bigger than 1 on the right half plane, real part of S bigger than 1. This is S equal to 1. So here you have a function. Now this function is the uniform limit of absolutely convergent sequence of holomorphic functions. So the limit is holomorphic as a result of this, because this thing. So it's holomorphic in the part of the theta 1. And this step was taken by Riemann, because this was defined by Euler before, but Euler was only on the real line. He did not have much access to outside the complex numbers. So, and then what Riemann did, he proved that this function has analytic continuation to real part, to complex plane, minus 1. Okay, so Riemann showed that real part of that zeta S has analytic continuation. To C take away 1. I mean, we cannot extend it to 1 because 1 is a singularity, because as S goes to 1, you can see that this series blows up. It converges to harmonic series, which is divergent. So there's no way you can extend it to the singular point 1, but it's an amazing fact that it has analytic continuation everywhere else. But not by this formula, because this formula is divergent. There's another formula for zeta that makes sense here and matches this one here. So that's the idea of analytic continuation. Now, this point S equal to 1 is a simple pole, and the residue of the function is 1. So S equal to 1 is a simple pole. This is known. Yeah, so it's a simple pole. What else is known? Another thing that's known is that zeta at negative even integers is 0. 0 for m bigger than 0. Yeah. So it has, these are called trivial zeros. So at -2, here, -2, -4, they're called the trivial zeros of zeta. And of course, Riemann hypothesis is that except for these trivial zeros, all other zeros are going to be on the real part of S equal to 1/2. That's the Riemann hypothesis. That's the first millennium Clay Math Institute problem, right? Okay. Now, so we also know the value at these other points. Well, actually, there's a general formula which was obtained by Riemann himself. the formula is that zeta, zeta of negative p is equal to, I believe, e p plus 1 in terms of Bernoulli numbers. P equal to 1, 2, 3, etc. I think it should be divided by p plus 1. Yeah. Should be divided. So this was this also we can derive it from Freeman's paper. This is not difficult. Well, I mean, after you do all that work, they follow. So is there a relation between this fact and this fact? And that's kind of source of a lot of fun formulas that people like to write. For example, people like to write yeah, 1 squared plus 2 squared plus 3 squared is equal to 0. And also they write 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4 which is 0. And all even powers of integers added 0. And what they mean by this is exactly the fact that, so because what is this? Formally, if you use the original definition of zeta, this is nothing but zeta at -2. So this is zeta of -2. But physicists like to see this as regularization of this series by zeta value. And if you regularize it properly, you can see. And that's a good idea. And this is zeta of -4. Now, what about zeta of -1? Well, this is like 1 plus 2 plus 3, right? Me. But our formula says that actually zeta of -1, so if I put this is p2 over 2, right? That's funny. So I've got the b2 over 2. b2 we calculated is 1 over 12, I guess. I think I made a mistake. b2 must be 1 over. Is it 1 over 12, 1 over 16? Because you know what this number is, right?
Yes, I'm not
Minus 1 over 12, yeah. But if I get yeah. So one of these formulas are incorrect. Yeah, so I have zeta of minus p is equal to minus pp plus 1 over p. It should be minus.
Is it over P maybe?
So it means, huh?
Is it just over P?
I have over p plus 1, but this thing that we got here, it could be over p actually. That's better. It would fit that, would solve the problem. So I'm willing to guess this.
From the theorem, it shows Bn is minus n times zeta of 1 minus n.
Say it again, please.
Oh, Bn is minus n times zeta of 1 minus n.
Oh, you mean zeta of
1 minus n times minus n is Bn, yeah.
I see. Yeah, I have. I'm gonna
Oh,
actually.
yeah, I think it's yeah, that's right. B plus one over P. Yeah.
I think it should be over P, yeah,
Yeah, that's right.
because it fits with that well-known folklore or whatever fun fact. This is one of those things you put on YouTube and then you get 1 million viewers for free. Yeah, so anyhow, that's all I wanted to say about this. Now, so now let me tell you a little bit about the idea of moduli. Okay, so basically I try to be on the right-hand side so far, and then we go. Now, what is a moduli space? The idea of moduli space. That's okay. So I think I'm going to erase everything here because it's better to be also focused on the center. So what is moduli space? Um, yeah. Yeah. So what is the moduli space? Okay. So I'm going to actually give you three answers in levels of sophistication. So the absolutely naive and kind of undergraduate definition I can give you, and that's more or less good for us. So basically, very naive and yeah, answer basically is that you have a set of objects, a set. I mean, this set could be, I will give you many examples, and you have seen this. Is a set of objects, and you have an equivalence relation on this set. An equivalence relation. So I emphasize this is an equivalence relation. So as you know, the definition on X. So then very often we are not interested in X, but we are interested in the quotient space. So then kind of a primitive notion is moduli space is this quotient space X divided by this equivalence relation. So basically what we want to know, this X is too wide, big set, but we want to study X up to some equivalence relation. So this is the set of all classes of objects, X, but X belongs to X, right?
Is there a natural topology on the space? Because
For now, there's nothing, but we will have natural topology and other things. Yeah. Now, let me give you an example of this that you see. Example is a classification of. So this is basically a classification problem up to isomorphism of objects. So classification of yeah of closed oriented yeah topological two-dimensional 2D manifolds up to homeomorphism. It's a classic problem that was solved in 19th century. So what is it? So basically, we want to study manifolds up to, closed oriented topological two-dimensional manifolds up to homeomorphism. And the theorem that was proved is the following. For any, okay, so the theorem is that any two-dimensional closed oriented topological manifold. So this topological two-dimensional manifold, etc., we call it a surface, a topological surface, right? Topological surface. Topology. Surface is homeomorphic. To a genus G surface. Genus G surface. Well, okay, so let me actually, it's not a good way to put it. So there's a better way to put it. This worried me. So let me put it this way. For any two, okay, so not any two. I formulated like this: two closed oriented topological surfaces. Yeah, this is a better way. Topological surfaces are homeomorphic if and only if and only they have the same Euler characteristic. They have same Euler characteristic. Or same, or equivalently, same genus. So we have this formula that the Euler characteristic of one of the surfaces is equal to 2 minus 2. So up to, we just put it this way, up to homeomorphism and up to topological classification, there is only one invariant which characterizes the surface completely, and that's the genus or Euler characteristic. So basically then here in this case, if we just take X to be the set of all surfaces, and that set, that equivalence relation is up to homeomorphism to be isomorphic up to homeomorphism. Then the quotient is just the set of non-negative integers 0, 1, 2, 3. right? So it's not quite a set because surfaces can be a lot of things, but that's a set of those oriented surfaces. And this thing in this case is homeomorphism. So this theorem that was essentially proved in 19th century is that x over this one then is actually 0, 1, 2. So in this case, we say the moduli is discrete. So there's a discrete moduli, which is this. So it's a discrete moduli. But a surface, so of course, I mean, this is denoted by such a thing. There's genus G. But a surface can have more structure than just topology. So this is a topological manifold, but you may wonder, what if I put the smooth structure? That doesn't change anything. Because, again, another fact is that any two-dimensional surface is a two-dimensional smooth manifold in a unique way. So there exists a unique smooth structure on any 2D surface, topological manifold. So now if I define X smooth, to be smooth surfaces, right? And if I define two-tailed smooth to be diffeomorphism, because it means it's smooth with smooth fibers, right? To be diffeomorphism, then we don't get anything new. So if you just do the same thing, then you're going to get, again, this set. So in other words, I can just say this is equal to X smooth over 2 Yeah. So we don't get anything new in this case. No new objects will pop out. In 4 dimensions, that's not the case. In 4 dimensions, there are more smooth structures, some of them called exotic structures, than topological ones. So there's much more. But in dimension 2 and 3 and 1, certainly there's nothing more. So this is all. But now I can put more structure. So we have topological, smooth. What extra structure you want to put now on this? Maybe we can classify up to that notion of equivalence, and then we'll see something maybe interesting. So what other structures you can think we put here?
Riemannian metric?
Yes, Riemannian structure is definitely one possibility. Yeah, exactly. I will consider that as well. What other structures?
Like a complex structure should be on any connected Herma service.
Exactly. Yeah, you can consider complex structures on them. And then something completely new happens. Completely new happens in that case. So, in other words, now, if I'm saying if you consider Riemann surfaces, if you consider this problem where X is the set of or the class of closed Riemann surfaces up to biholomorphism, then this is not a discrete moduli at all. It's a huge space. And that's something that Riemann was the first person who understood this, actually. So let me now put it here, which is quite strange, actually. And so now let X be equal to, again, set of all those Riemann surfaces. And due the isomorphism that comes from holomorphic bounds, not smooth holomorphic bounds, biholomorphisms. So a map F from one Riemann surface to another is called, it should be bijection, 1, 1 on 2, right? Holomorphic. And then it follows that the inverse is also holomorphic, but we can even put it as a condition, but it follows from these three conditions. And F inverse holomorphic.
Will it do the X form a category or
What's that?
does X form a category?
Yeah, it is a category indeed. It is a category. I mean, you have this morphism, you can compose them. And in fact, I just look at with biholomorphism too. So then X over this is not discrete. It has a very complicated structure. That's an example. Is an almost manifold. Manifold. So the dimension of this manifold was computed by Riemann, essentially. So this is called now G. Well, okay, so now closed Riemann surfaces of genus G. Let's fix the genus. I'm going to fix the genus G. Okay. So this I call it xg then, and then the quotient I call xg divided by this. So this is the modular space of genus G Riemann surfaces, closed Riemann surfaces. Yeah. Yeah, Riemann studied this space. And he proved that actually for G bigger than or equal to 2, he gave a formula that dimensional. He showed that, first of all, this is essentially a complex manifold, which I don't get into that much right now. But its dimension over C is equal to what's the dimension? Is it 2 minus what is the dimension of this? Anyone remembers? 2 minus is it 3G minus 3? Huh? You want to check? Is 3G minus 2. Could be 3G minus 2, isn't it?
What is an almost manifold? Is it not Theorem of that?
Huh?
What is an almost manifold? What?
Yeah. Yeah, it is the quotient of a flat in a very nice space by a discrete group. So there will be some orbifold points.
3G minus 3.
3G minus 3? Okay. So this is the dimension over complex numbers, and over real numbers, we multiply this by 2. Okay, so to see this, we have to work hard. I mean, we're not going to prove this, but this is the thing. But here I have in Zagier's theorem, I have also not just this one, I have mg1, not mg. So let me tell you what is mg1. And in general, let me tell you what is mg. So in general, then what you want to do, you just take a Riemann surface sigma plus n marked points. So these are like labelings that we had for our graphs. Now we are also having labelings plus n marked distinct points. So these points, I call them P1, P2, Pn, right? So now for me, x is going to be so now this time we're going to study this x is the set of all sigma and these marked points, P1, Pn's, sigma closed Riemann surface of genus G with n marked points. This, but then the notion of equivalence is changing now. So it's going to be a biholomorphism, but this biholomorphism should also respect the mark points. So F from sigma P1 Pn to, so I call them maybe sigma 1 to sigma 2, say Q1 Qn. So, I mean, F is biholomorphic, like as before, but it has to respect these points. So, yeah, these labels are important. First, F of Pi is equal to Q.
It's like a pointed set.
Yes, exactly. These are n-pointed Riemann surfaces. The pointed set, like in topology. Exactly, yeah. So you just take this x now, so I call it xgn, such things, and I divide by this equivalence relation, and that's ng.
Does ordering matter here? Or PI?
It's equal to, it's equal to xgn divided by this. Sorry?
Does ordering matter here? Can a PI go
Yeah.
to K or something?
No. No. I mean, it should be f of pi should be q. It's so rigid, and this gives us a lot of good instruction. So I don't think I should define. I need to define what is a Riemann surface. So Riemann surface, the definition is like a smooth surface, but the maps have to be holomorphic. Okay, so now, but still, I mean, the question is we have to have a good understanding why we are getting this sort of continuous moduli now. Instead of discrete set of equivalence classes, all of a sudden, we are getting a continuous module. Why? That's very strange. This is a very peculiar thing of holomorphic functions. Let me give you an example so that you see why continuous moduli appear. So what continues? I mean, the simplest example that tells you that there is a big difference between the smooth and holomorphic things is that so it's a warm-up, basically, not really answer to this question, but the warm-up example is the following, that in the complex plane, the open disk and the whole plane are not biholomorphic, but they are diffeomorphic. B2 z such that absolute value of z is less than 1, and the C are diffeomorphic. But not biholomorphic. Right? Why that's the case? Because in usual topology, the open unit disk and the whole plane, they are diffeomorphic to each other. You can write a smooth map, C infinity map from here to there, vice versa. But you cannot write the holomorphic map equivalence between the two. What goes wrong?
Something about boundedness? Yuval's theorem?
Yeah, exactly. If you look at the inverse map, it's a holomorphic map that is bounded. And by Liouville's theorem, we know that this is to be constant. So Liouville is like a police. It ties your hand completely. Immediately stops you from claiming this map. Yeah. I mean, this is not an example of this continuous modular, but it's something, it shows that there are things in the holomorphic world that have no precedent in the smooth world or continuous world. But then there's a real example is the following. So I'm going to define now a series of Riemann surfaces, not closed, but that's okay. So I just take a disk of radius 1, and then I take a disk of radius r. 1, r. So this r is bigger than 1. So this dr, this dr, the set of all z such that absolute value of z is less than r is bigger than 1. It's obviously a Riemann surface. It's not closed, but that's okay. But it's a Riemann surface. So then there's an exercise in holomorphic functions that asks you to prove this. dr is biholomorphic to dr prime if and only if what? When two of these annuli, so maybe I call it AR because this is better name, annuli, AR, and this annuli, AR part. This annuli AR is biholomorphic to annuli AR prime if and only if R is equal to but in the smooth world, all two annuli are diffeomorphic. So what you see then is that you see a continuous family of non-isomorphic, non-biholomorphic Riemann surfaces. And this is quite drastic. So they are different from the point of view of Riemann surface theory. Not the same. And this is kind of germ of the 10-bit Riemann surface things. Okay, now any questions?
What in the case of n marked points,
Yeah.
would we also quotient out the permutations of them, so that they're just fixed or instead of preserved?
No, if you quotient out by permutations, you get a different moduli space. Not this one, yeah, but you can quotient it. But then in that case, you have to allow that the map permutes these things among itself. So in this case, we don't divide. Yeah, I think so. Yeah. Yeah. So let me give you two more examples of that you see that the moduli, the continuous moduli actually appear in a natural way. By the way, these spaces are not compact. And they have to be compactified in a special way, but they're not compact. Yeah. So let's look at one more example, two more examples actually. Yeah, because there was a question, so let me look at the example of this actually. Yeah. First of all, it is a non-trivial theorem. I mean, when you take a course in Riemann surfaces, usually you prove Riemann-Roch theorem first, then you derive this fact as a consequence, as I'm writing, that on the sphere there exists a unique complex structure. So on Riemann sphere, on the Riemann sphere. Okay, so no, so yeah, on a closed surface of genus G, there exists a unique. So, so let me put it, there exists a unique Riemann surface, or unique up to biholomorphism, of course. Of the biholomorphism. Riemann surface structure. On a surface, on a closed surface of genus G, of genus 0, sorry. And that space, we call it CP1, which is the complex projective line. So this is CP1. This is the Riemann sphere or complex projective line. So yeah, so on the sphere there is, I mean, on a topological sphere there is only a unique Riemann surface structure. So this basically means that what M0 is just 1 point. Just 1 point. Yeah. Now you may want to go to genus 1. So what is M1? And one is much more complicated. You can show that again, this needs something like Riemann-Roch and Abel-Jacobi map and this stuff, but any closed Riemann surface of genus 1 is isomorphic. By isomorphism, again, I mean biholomorphic, is isomorphic to a complex torus. So this torus is which is C divided by gamma lambda. So torus X. So X is isomorphic to C divided by lambda. The lambda is a lattice in the plane. Lambda is equal to Z tau 1. Okay, Z tau. Okay, Z is Z tau, where imaginary part of tau is positive. So this lattice is going to look like this. So you have here one generator you can always arrange to be 1. The other one you can arrange to be in the upper half plane, tau. This is called modular parameter. And then you create a lattice that's generated by these two vectors. It's a linear combination, integral linear combination of this and that. So you know what to do. You just complete it into. Yeah. So we have this now. So these are all the. So, well, I mean, C is a complex manifold itself because naturally the most obvious complex structure. And this is a discrete subgroup. There's a quotient map, and on the quotient map, it gives you a complex structure here. But the thing is, so let's call this lambda tau. And let's call this x tau. Now, the thing is, 2 of these things are biholomorphic if and only if. Okay, so there's a second part of this. X tau is isomorphic or biholomorphic to x tau prime if and only if there exists a matrix G or matrix A, which is equal to A, B, C, D, belonging to to Z, this modular group. It's called the modular group. Such that A of tau is equal to tau prime. In other words, such that A tau plus B over C tau plus D is equal to F. So under the action of the Mobius group, so it is the just integral linear things, not the whole Mobius group, but just okay. It's just this one. So what does this mean? If you believe these 2 facts that I mentioned here, it just means that the modular space of Riemann surfaces, closed Riemann surface of genus 1 is equal to upper half plane divided by action of the surface. So let me now write it. So this is M0. Now I'm writing M1 for you. So M1 if you believe those two facts, you get that M1 is isomorphic to H divided by SL2Z. Where H is the set of all tau belonging to complex numbers, such that imaginary part of tau is positive. And this is also called Poincare upper half plane. Poincare upper. Okay. And this group SL2Z that we are going to work with it very soon, this SL2Z is acting on the Poincare upper half plane in the following way. So what is SL2Z? Let me write it again. Is the set of all A equal to A, B, C, D, such that AB minus BC is equal to 1. That's for the S part. And these are integers, A, B, C, D. Belong to this. And there is an action of SL2Z on the upper half plane, right? Which is given by that action here. So we are looking at quotient space of upper half plane. But so there is a exercise here. You check that actually, if you have something whose imaginary part is positive, the imaginary part of the image is also positive. So imaginary part of tau positive implies that imaginary part of A of tau is also positive because you can compute imaginary part of this guy. In terms of imaginary part of tau, and that's going to be positive. And this condition, AD minus BC positive, is important. So you may wonder what kind of space is this? What is this quotient space? Because this is the upper half plane. And we are dividing the upper half plane by that. And the quotient in this case actually is called the modular curve. It's called modular curve. And it's like this. So there is this circle of radius 1. Zero. And then you have this half here. You have negative half here. So basically, you can show that any point in the plane is congruent under this map to a unique point here, except that this point is congruent to this point because it's given by translation for one, right? So basically, it's going to be equal to this thing. This is strip folded along its boundary. So if you, this point is congruent to that point under this map because there's translation by one. You see, here there is also here this map. I mean, there are two maps, S and T. T of Z is equal to Z plus one, translation by one, and S of Z is a polar map, minus one over Z. And the thing is, actually, these two things generate S and Z, T, both belong to SL2Z, and they generate the generators. Okay, so this group is generated by these two things. Actually, it's a free product of group of yeah. So let's not go into that. But this is space, this modular curve, which we denote by M1, is the first non-trivial modular space. I mean, this point is a very special point. These points also are very special, these 3 points. Of course, there's point additivity, that's for sure. Okay. But now you may wonder, how can we ever understand M2, for example? What would be the story for surfaces of genus 2? How does it look like, even? How these guys look like, it says. Okay, to get into this, we need a little more work to do. I'll do next lecture, but that's okay. But maybe I will just finish with one more example, but this time I'm going to take marked points to see what's going on. Okay, so yeah.
Is this action of SL2Z on H be special? Is it like free, proper, anything like that?
The action?
Yeah.
Yeah, so the action is not free. That's a good question. The action is not free because this point, actually, the stabilizer of that point is a subgroup of order 2, I believe. Certainly, this is fixed under S. This is I, right? And if you look at that, S of I is equal to I. Because minus 1 over I is I. But there's no other, so the stabilizer of I is consists of, this is subgroup of order 2. Now, what about this point? This point? I mean, well, I mean, what is this point, by the way? Okay, so what is this point? So this point, maybe we call it rho. Yeah. You believe me that this angle is going to be what? 60 degrees. So that point is going to be e to the 2 pi I over e to the pi I over 3. So what is the stabilizer of this rho? Yeah. What is the stabilizer of this rho? Yeah.
It will still be like 1 comma S.
Again,
At least S will be in there.
S is there. So let's look at this guy. So what is S of rho? Well, it's minus e to the negative pi over 3, right?
Okay, yeah,
So it's not that. Yeah, but it has a non-trivial stabilizer. Okay. We can actually try to find it. Why not? So I'm going to look at some, well, some ABCD, right? Such that A rho plus B over C rho plus D is equal to rho, right? So if we do cross multiplication, you get A rho plus B is equal to C rho squared plus D rho. So we have got C rho squared plus D minus A rho negative E equal to 0, huh? But what is rho squared now? Yeah, rho squared into the negative 2 pi I over 3. No, into the 2 pi I, that thing. Right? So that's yeah.
That's just the other point.
Hmm?
That's just the other point over there.
That goes into the other point, right? I see. Yeah, and yeah, that's right. That's the other, yeah, exactly. That's the other point. Yeah. Okay, so I think I'm gonna leave it now. We can, it's a good exercise to think what is the stuff. I know it's not trivial. I believe it should be in Z3. But nothing immediate comes to mind. What was your question?
just is it free or like is
Yeah.
the action free proper?
Yeah, it's not free, but otherwise it's actually good. I mean, it acts properly. Yeah. 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 So let's look at one more example and then we'll meet for today. So this example again, we are looking at x equal to C1, and then we just take 1 point. So like 1 marked point. So there is a fact about Mobius time. So first of all, I mean, automorphisms of CP1. What do we mean by automorphism? I mean, all biholomorphic maps from CP1 to CP1. Biholomorphic maps from CP1 to CP1, they are actually completely known. This is the holomorphic symmetry group of CP1, and that thing is just Mobius transformations. So this is the set of all. I'll put it this way now. This time, ABCD, such that A, B, C, D belongs to complex numbers. That's a big thing. A, B, C, D belong to C, and AD minus BC is equal to 1. And again, this thing acts by Mobius transformations on this one. So this action has a very peculiar property. The property is that actually for any 3 points, it's 3 transitive reaction. Any 3 points can be uniquely mapped into any other 3 points. So for any 3 points, 3 distinct points, P1, P2, P3 belonging to CP1, there exists a unique A equal to belonging to automorphisms of CP1. A unique Mobius transformation such that A of 0 is equal to P1, A of 1 is equal to P2, A of 3 is equal to P2. So any 3 points can be uniquely mapped to any of the 3. This is called tree-transitive. The action is tree-transitive.
Is that infinity or is that infinity?
That's it. Oh, that's infinity.
Yes.
That's infinity. Very good. So the action is tree-transitive. Okay, so then it follows that actually M03 is just one, has only one thing, because any two Riemann surface of genus 0 with 3 marked points is isomorphic to any other. There's only one actually object in this modular space. But if you go to one more higher, now that's kind of interesting. M04, what is that now? That's an interesting space, which I let you think about it, but this is related to cross ratio. So we know that 4 points can be mapped to another 4 points if and only if the cross ratio of these 4 points are the same. So I won't write it down, but it's related to a lot of nice stories about projective geometry. Yeah. It's classic geometry. So we look at this. So this space has become interesting and nice. Actually, this could be that this is actually same as CP1. Most probably it's just there is one parameter which fixes all these things. So we just okay. So I think so. Now we have some understanding that this modular space notion, and I haven't defined the actual definition of modular space. That's a bit more subtle than saying that. Yeah, we are taking quotient spaces. It's really about smooth families or holomorphic families of parameterizing objects. And it's like a configuration space of things in physics. So sometimes, yeah, configuration space is a space that parameterizes the states of a system. And this parameterizes the states of Riemann surface. Somehow similar. Okay, well, thanks, guys. So if you don't have any questions, I just say call the Zoom off then. Thanks very much. Are there any questions?